Now, reinforced concrete foundations. You are aware that foundations are classified as shallow foundation as well as deep foundation, and details regarding the foundation and soil characteristics you have gone through the syllabus of geotechnical engineering, that means in soil mechanics and foundation engineering as well as geotechnical engineering. So in the design of RCC foundations, let us first of all go through shallow foundation. Now, shallow foundation are generally used when the soil on which foundation is to place is of sufficient strength and is available at a relatively short depth below the ground surface. So that means if the soil of good bearing capacity is available at a shallow depth, then the depth of the foundation will be lesser, and that type of foundation are termed as shallow foundations. Now, some of the shallow foundation types, as the foundation for a wall, that is strip wall footing, continuous wall footing, isolated footing for column, combined footing for column, raft footing, or mat foundations. So in the current curriculum, we will be going through the design aspect and design detailing of isolated footing for column. Isolated footing for column mean a single footing devoted to a particular column, and there may be isolated footing for a number of columns. That means if a column has its own footing, so that is isolated footing. And when we are combining the footing of two columns or more than two columns, so that will be combined footing. And if the number of columns are more, then there may be raft footing or mat type of foundations. Now, deep foundation. Deep foundation are required when, in comparison to shallow foundation, when the soil below the ground surface is not strong enough to take the loads coming from the superstructure, and this necessitates the transfer of load to a greater depth. So that means if the soil beneath the wall or column, whatever be the mechanism to transfer the load, that means if soil is not such strong, not having sufficient bearing capacity which can take care of all the loads coming from the superstructure, and then we have to go deeper into the soil so that we can come across with a suitable soil having suitable bearing capacity, or some solid type of rocky type of material is available where we can transfer the load. So that type of foundation which are having a sufficient depth, then they are known as deep foundations. In general, pile foundation, caissons, and other type of well foundation, etc. But in our syllabus or in our curriculum, we have to go through the isolated footing as well as combined footing, particularly for columns. Now, reinforced concrete shallow foundation, isolated footing. Isolated footing generally provided for individual columns, where columns are to be located on firm soil. That means that load of the column or the load which is transferred by the column is located on a soil which is very firm and having good bearing capacity. such that that soil which can take care the load from the column without any type of failure. In other words, we can say when the bearing capacity of the soil is sufficiently good to take the load coming from the column. Now, isolated footing is in general of square or rectangular plan. It may be of trapezoidal type of footing as per the requirement, but in general, if we are talking about the isolated footing, they are either square or rectangular in plan, which comprises of a thick slab of uniform thickness and may be flat, stepped or sloped such that the load is dispersed as a uniformly distributed load on the soil below. So that means isolated footing is designed in such a way that the foundation is also a slab, and on that slab column is placed, and column will transfer the load to the slab, that is called as footing, and the load coming from the column will be uniformly distributed on the soil beneath the footing so that load can be transferred without any type of failure or without any type of differential settlement. That means if there is any settlement at micro level, then that settlement will be uniform. So this is the purpose of the design of isolated footing. Now, permissible pressure on the soil beneath the footing is called safe bearing capacity. Now, the area of the base of footing is decided considering the safe bearing capacity as a UDL, uniformly distributed load on the area of footing, such that the pressure on the base of footing due to loading of the superstructure and column should preferably be lesser than safe bearing capacity of the soil available. Now, if you see in this first figure, here is a column. Column may be rectangular, or it may be square column, or it may be a circular column. Now this column, this one is the column, and below there is a slab which is called as a footing. And when we see this plan, in plan, if you see, this is a rectangular type of footing. It may be a square type of footing, and it is a totally a flat footing, flat slab type, and column is placed on it. Now in this figure, you can see that column is transferring load in the form of steps. That means footing is in the form of steps. This is one step, this may be another step. A number of steps may be there, and the load of the column will be first of all transferred to the upper step. Then this upper step will transfer the load to the lower step, and ultimately load will be safely transferred to the soil. So this type of footing is known as stepped footing. Now sometimes we design these type of footing where we will be providing some slope for the purpose of economy, because we are aware that bending moment will vary as we move away from the column. So accordingly we can design the footing, and this type of footing will be a sloped footing. You will be seeing that there is a slope, and this will be the plan of the footing. So three type of footing we have decided. One is flat footing, second is stepped footing, and third one is sloped footing. And flat footing may be square in size or rectangular in size. Now combined footing. Combined footing is a single footing for two or more than two number of columns. When it is not feasible to provide isolated footing for each column, maybe due to inadequate area available in plan, due to which isolated footings may be overlapping. When two or more columns are located close to each other, then the bearing capacity of the soil, if bearing capacity of the soil is low, then larger area will be required for the footing of each column, and due to which the footing from each column may be getting overlapped with the footing of the other column. Now, combined footing term is used when two number of columns share single footing, and the term continuous footing is used when more than two columns are in a line. Combined footing becomes necessity when one of the column is located at the property line. That means if there is column is touching at the property line, then it is not possible to construct a footing for that particular column as an isolated footing, because 50% or more than 50%, 50% or less than 50%, we can say, portion of the footing will be going towards the adjacent plot, which is not acceptable. So that time we have to design a combined type of footing. Now you can see in this figure we have shown two number of columns, and both the column having a common footing, and that is known as combined footing. Now if you see, suppose we want to put the footing for column number 1 and column number say 2 individually, then what can happen, that this footing may be for first column and this footing may be for second column. Then you can see that here in the some portion footing of each column are getting overlapped with the footing of the other column. So to avoid this, we have to design combined type of footing. Second case we have taken into consideration when one column is okay but other column is just at the property line. So then it becomes the necessity to design a combined footing when one of the column is touching the property line. Now, mechanism of load transfer through the foundation, how load is transferred to the soil. First type may be when the column is concentrically located on the footing. So that time load will be concentrically loaded footing, we can say. In concentrically loaded footing, now you can see here this diagram. Here we have taken a column and this is the footing, isolated footing, and you can see here that total load of the column or the line of action of the column load will be coinciding with the centroid of the footing. So that means there will not be any eccentricity. So we will say that this footing will be designed for a concentrically loaded footing, and load is just concentric. That means load is just passing through the centroid of the footing below the column. So it may be a rectangular type of footing or it may be a square type of footing. So we can find out the area of the footing by multiplying both the dimensions, whether it is a square or whether it is a rectangular. So what we want to say here, the line of action of the load from the column coincides with the centroid of the footing. Soil pressure is assumed to be uniformly distributed as we have shown in figure. Now this pressure is uniformly distributed, it is just like UDL. Soil pressure we can calculate by, if P is the soil pressure, then it will be total load divided by area of the footing. And the allowable soil pressure we can calculate from the value of safe bearing capacity. That means what will be the safe bearing capacity of soil, and from that by applying some partial safety factor we can find out what will be the allowable bearing capacity of the soil for this footing. Now area footing required, we can calculate the how much area of the base of the footing is required. That will be the ratio of total load on soil divided by allowable soil pressure, as already have told that allowable bearing capacity of the soil. And total load will be calculated by the addition of load from the column plus self weight of the footing, that is load of the footing. Now the mechanism of load transfer through the foundation: when loading coming from the column is having some eccentricity, that means it is eccentrically loaded footing design. Now when it will be eccentrically loaded? When the line of action of load from the column do not pass through the centroid of footing and have some eccentricity E. Then, or the column may transmit a movement along the vertical direction. Now we can see this diagram. Here you will see that column is transferring load vertically downward, as well as there may be some movement. That means there may be transfer of some movement. Now it will be the case of just combined type of loading. That means direct vertical load is there, as well as movement is acting, and due to this movement there will be stresses, and vertical stresses will be due to the load. Now you see the diagram here, pressure diagram. You will see that load is vertically downward and movement is acting in the clockwise direction. So you will find that due to this movement there will be some eccentricity, or we can consider that this is one load and another load you can consider due to the movement by some eccentricity, and accordingly the pressure diagram will change. You will see now pressure diagram is not a uniformly distributed load, it is a trapezoidal type of the load. That means intensity of the pressure varies from one end to other end, and when we get the total load, that means what will be the resultant load of this diagram, then this load can be shown like this. This is the total pressure due to this trapezoidal type of pressure diagram. So that means it is acting at some eccentricity E. Now you can see here the centroid, this will be the line passing through the centroid of the foundation, but the line of action of the pressure is at a distance E from the center line diagram or center line of the footing. Column may have, another case is column may have its position eccentric to the centroid of the footing. That means this column may be located somewhere here, or this column may be located somewhere here. Column may have some horizontal load in addition to the vertical load. That means if some horizontal load is acting on the column, it may be due to any type of horizontal forces. That means forces parallel to the horizontal, just like wind pressure, or it may be earthquake forces. Now the footing is designed in such a way, this we have to keep in mind, that when we are designing footing, then we will design footing in such a way that the resultant load should act in the middle third region of the footing to avoid any type of tensile stresses, or you can say uplifting of the footing. Now this movement may develop due to position of the column. That means if you change the position of the column, then eccentricity may happen, or due to any horizontal forces acting on the column. So this type of loading will be known as eccentrically load. That means, and this type of footing which we are going to design, this type of footing is known as eccentrically loaded footing. Now let us go through design steps when we have to design an isolated footing Particularly here we are going through the design steps for square footing, or it may be a rectangular footing as per the guidelines of Indian standard IS-456. Now footing shall be designed to sustain. If you refer the clause number 34.1, so clause number 34.1 states that footing shall be designed to sustain the applied loads, any movements and forces, and the induced reaction if any, ensuring that any settlement, if there is any settlement occurring, that shall be as nearly uniform as possible, and the safe bearing capacity of the soil should not exceed. So this is the principle of the design of the footing. That means footing should be able to transfer all type of loads coming on the footing to the soil, such that if there is any settlement, that settlement must be uniform settlement, so that there should not be any turning of the foundation, any rotation of the foundation. And another thing which is very important, it should never cross or exceed the safe bearing capacity of the soil. The major design aspect of footing relate to, very important is design for flexure, and the second important aspect is design for shear. Now here, when we will design isolated footing, we will design for shear both in one-way shear as well as two-way shear. One-way shear in general, we design any type of beam, and two-way shear we use to design in case of flat slab, and it is also known as punching shear. And another important part is we have to take care of the bearing as well as the bond. Now step number 1, first of all we have to do the calculation for the loads. Now let us consider P is the load from the column and P1 is the self weight of the footing. Now self weight of the footing we can assume 10 to 20% of the load coming from the column. Step number 2 is depth of the footing. That means what should be the guideline for assumption of thickness or depth of the footing. We can refer clause number 34.1.2 of IS-456. Now the thickness of footing slab can be decided based on shear as well as flexure at a critical section near the column, and for that we will look after the guidelines given in the IS-456. In general, the shear is more critical for deciding the thickness of the base slab of the footing. Now minimum thickness at the edge level of footing may be taken as 150 mm. That means the thickness of the footing should never be less than 150 mm. And the minimum clear cover as per IS-456 is 50 mm. So this is the minimum cover, and for practice purpose, when we will be going to design any problem, we will be taking the minimum clear cover may be more than 70 mm. Now step number 3, here we will decide the size of the footing. That means what should be the area required of the footing so that the load from the column as well as self weight of the footing can be transferred to the soil without any type of failure. Size of footing can be calculated from the allowable bearing capacity of the soil and total load of the column as well as self weight of the footing. Now how to find out the area of footing base? So required area of footing base, we can take this formula. Here P is the load of the column plus P1 is the self weight of the footing. So combined load will be taken and divided by QA, where P is the load from the column and P1 is the self weight of the footing, which we will be assuming 10 to 20%. We can assume 15%, 18% as per our requirement. And QA is the allowable bearing capacity of the soil. After that, we will calculate upward soil pressure. So upward soil pressure is QU, that will be the factored load divided by whatever be the area of footing we have provided. First of all, we will be finding what is the area footing required. Then accordingly, we will decide whether it is a square footing or a rectangular footing, and by approximating the size, we will be deciding the size of the footing, and that will be known as area of the footing provided. So when we take the factored load divided by area of footing, which we have provided, actual area of footing provided, then we can calculate the upward soil pressure given by QU. Now step number 4, as already we have told that depth we have to check. First of all, we have provided the depth. Now we will be checking it for flexure as well as shear, and very critical aspect is shear, and we can refer clause number 34.2.4. Now one-way shear. For one-way shear, the critical section can be taken at a distance D as per the IS-456 from the face of the column and perpendicular to the plane of the footing slab. And accordingly, the effective area resisting one-way shear will be rectangular if the footing is square or rectangular in size. If the column is square, then we can go for the square type of footing. If the column is of rectangular shape, then we can go for the rectangular size of the footing. Accordingly, at a distance D, that is effective depth of the footing from the face of column, we will mark the critical section, and then we will be calculating the effective area which will be resisting the shear. So from that we can find out how much is the shear force VU is at the critical section. Then after finding out the VU, we will be assuming a suitable percentage of steel as per the code limit. That means we will be going to the table number 19 of IS-456, and from table number 19, what we will do, first of all, we will be assuming some percentage of steel within the limits prescribed by the Indian Standard Code, and from that percentage of steel and taking the grade of concrete from table number 19, we can find out what will be the shear force which can be registered by concrete. Now this VC must be greater than or equal to VU. So depth required is find out by using this formula. We can find out the depth required and check with the depth which we have provided. So this will be the, by applying the one-way shear check, we can find out how much is the depth required, and then we can compare it with the depth we have already provided. Now check for depth for two-way shear, which may be called as punching shear, and this I have taken from the previous lecture. In case of flat slab, we can take the same methodology and go through the two-way shear check. Thank you.